Alright, so here we are with Unit 12, lesson number, I believe it is 6, and this is on what we call half-life. Um, Basically, this is related to what we had talked about earlier when we talked about alpha, beta, positron decay, and substances that are radioactive undergo decay at a constant rate, which is called its half-life. And sort of kind of miscellaneous points would be this, that the half-life of a substance is constant, meaning that the half-life of an element does not change, and it cannot be affected by temperature changes, pressure changes, or concentration changes. So for example, if an element's half-life is 2 minutes, there's nothing that we can do to that element to change its half-life. It's always going to be 2 minutes. Doesn't matter if we heat it, put it under pressure, or add more substance, the half-life of that substance is always going to be 2 minutes. And what exactly is half-life? Well, half-life, if you look at the definition, is the time it takes for half of the sample to decay into a new element. Now, in this section, we don't care what element it changes into. We were in lesson when we talked about alpha and beta decay. In half-life, we're not interested in what it decays into. Most of the time, what we're interested in is how much is left after a period of time. Now, the other thing is, if you look at table N, this is table N here. It's also in your reference tables. We've already talked about decay mode. Decay mode tells you whether something undergoes alpha decay or beta decay or positron decay. That's all that tells you. And you do need that for the section on alpha, beta, and positron decay. We don't need this for this section. We're interested in the half-life. This column tells you how long each half-life is for different elements, and they can range anywhere from milliseconds to literally, if you look at the bottom of this table, some elements like uranium and polonium have half-lives of billions of years, which means they decay very slowly, which means they're basically around forever. So let's take a look at how you would use this. And let me give you an example here. We'll just make it easier. Let's say we have element X, just going to make up element X. And let's say element X's half-life is 10 years. That's its half-life, which means every 10 years half of its sample is gone. So the typical question would be this. If I have today, let's say I have, I'll just make up a number. Let's say today I have 60 grams in 2014. How many grams would I have left in the year 2034? Okay, and the way that you do that is you set up a table like this. And I know in your reference tables they give you a formula for half-life. I don't think it's really very useless. This is what I always show my students. But you're welcome to use that formula if you want. So here's our starting time, 0. That's 2014. And I'm starting with 60 grams. And I want to know how much of that 60 grams is still going to be remaining in 2034. Well, after one half-life, which is 10 years, right? That'll be 10 years. That'll be 2024. I'm only going to have 30 grams left. After another 10 years, it'll be 20 years, and that would be 2034, which is what I'm looking for. I would have only 15 grams left. And that's in essence what you have to be able to do here. One of the other things they will say to you, and they don't do this a lot, is they might say, well, instead of the mass, what fraction of your original sample is left? Well, all you have to say is, after one half-life, I only have half of my original sample left. After a second half-life, I have a quarter of it left. And all you have to do to cut this in half is double the bottom number. The next half-life would be an eighth of my sample. Or they could ask you percentage, right? This would be 50% of my original sample. This would be 25% of my original sample. That's the most common problem they give you. If they want to be really mean, they could give you the mass at the end and ask you to work your way backwards. So one of the things you have to remember is that what you're doing in this column, and you might want to write this down, what you're doing in this column is you're adding the half-life each time. No matter what the half-life is, it could be years, months, seconds, you're adding. What you're doing on this side is you're cutting that number in half. If they ask you to go in reverse, then what you would do as you go up is double the number. Okay? Those are the most common things that they would ask you. You have to remember, if you're going to use this method, that this always starts at 0. So this does not count as a half-life. The next one counts as a half-life. And, I was looking through the problems that he gives you, and again, I don't really like them very much. because first of all, the chromium 51 is not even on reference table N, so I don't even know why you would actually put that, and I will have to change that eventually. So what I'm going to do is I'm just going to go right to number 3, which is a question on the half-life of carbon-14. Carbon-14 is on reference table N, so I'm going to do this one. And what it's saying is what mass of a 100-gram sample of carbon-14 will remain after approximately 23,000 years. So I am starting with 100 grams of carbon-14. And they want to know how much is left after that. So I have to go and look at the half-life. The half-life of carbon-14 is 5,730 years. So like my previous one, I have to add 5,730 each time. So after my first half-life, okay, I don't know what's going on there. So let me go back again because for some reason it's not working. All right, so here we have this again. 0, 100 grams. So after one half-life, which is 5,730, I would have 50 grams left, or half of my sample, right? After another half-life, which would be 11,460, I would have 25 grams, or a quarter of my sample left. Okay. After another half-life, which would be 190 years, so a long time. It turns out that, yeah, I know, it's, sorry about that. So again, I'm going to go through this. And obviously I think you can see hopefully that after 4 half-lives, which would be about 23,000 years, I'm going to have, well, one half-life was 50, 25, 12 and a half. So after 23,000 years, I would only have 6.25 grams of my original 100 grams of carbon-14 left. So that'd be half of it, a quarter, so I'd have an eighth of it left. And I think, let's just go through the next one here. Hopefully I can get it to work without it messing up. Alright, so now this is a question where they're actually asking you to work in the opposite direction. So they're giving you iodine 131, and it says now if 1.25 grams of that iodine remains after that amount of time. So now what they're giving you is how much is left at the end, and you have to work your way backwards. So let's try that one. This is a little bit tricky. So let's go back and look at, on table N, the half-life of iodine 131 is about 8.07 days. So let's go back to the question. So we're going to do the chart that we had done before. So here's our sample. So again, remember we're working backwards now. So it's 8.07, so 8.07 would be half of our sample. That's one half-life. If we go, that would be 16.14. That would be 24, whoops, point 21. If we keep going, 24.21 plus 8.07 is 32.28. 32.28, and I'm assuming that the last one would be 40. It might be off by a little bit because the numbers when he made this ditto up might be a little bit different, but that's when we're going to have 1.25 grams left. Now we got to work back, which means you have to double. So doubling that would be 2.5. That would be 5. Oh, man. That would be 5. That would be 10. That would be 20. You're not done yet because you have to go back to your original, which would be 40 grams. So our original sample would be 40 grams. And again, I don't want to make this much longer. It's already almost 10 minutes, so we will certainly go over more problems.